So to abstract them both together, I've just drawn these pictures. And with pictures, you can be very abstract and vague, you know. And, you know, when people say pictures worth 1,000 words, you know, I always smile because, you know, the pictures are easier sometimes than the words. So I just have messages and arrows going. But, you know, there's a notion of messages being produced, and there's a notion of message being consumed. I mean, that's what I'm trying to do with these pictures. And the question is, what does a consumption of a produced message really mean? Right? So what is the, and in remote assignment, the message is data to be remotely assigned to a variable. Okay, so what you're sending is an expression. Okay, and what you have declared in the receiving process in the port somehow this is associated with the port. Okay, because somebody's sending to a port, so from that port we are going to some variable. Okay, and either through the port or through a receive call, we'll see what that means, and is getting assigned to a variable. Okay, so the result of send is to assign a sent expression. I didn't correct it, to some variable in the remote process thread. Okay, and you know the type of expression could be just a word in Xenu. It's just all you think is a word, or you can imagine there being some typing there. And there have been languages that have talked about typed assignment also. Okay, in fact, that's what object communication is about. Okay, and I'm going to now the mother of all distributed languages, more or less, or I shouldn't say distributed, it was concurrent. These were really threads in a single process, but inter-thread communication is a lot like inter-process communication. Okay? We saw in Xenu you have threads, but similar to what we might do in Unix. So this was very clearly, you know, even though they didn't call it remote assignment, he called it message passing. This is Tony Hoare. And you said this is bound port. So the communication was not like Xenu where you were passing an int value to multiple processes. The receiving process could receive values from multiple senders. Okay? You said send to process P this expression. Okay? And here you said receive from process Q this variable. And basically these completed when this expression got assigned to this variable. Okay, this is a very influential language, CSP, and you know, the basic construct here is presented here. Okay? And in the case of remote procedure call, the message is a request. It's not data, it's a request. Okay? And that has to be, is you're telling somebody else, please. That's why we often talk of the receiving process as being a server. Okay? And that makes sense only when you're sending a request of some kind. Okay? It might be a server or some data storage, but it really makes more sense there. Okay? By the way, CSP was meant for parallel processing also. So it was not server-client, it was just a bunch of processes cooperating together, computing, multiplying matrices, for instance. That's the classic parallel computing example. Okay? And so what you're sending is, a request means you're sending some request name, some parameters of the request. So effectively you're sending information about what method is to be called and what the parameters of the method are. Okay? That's what you're sending. I mean, that's what RMI is doing when you make an RMI call. And that is what is queued in the port. And the result is to execute some method in the remote process. Okay? And usually it's built on top of object communication because you're sending these typed values. Okay? So that's RPC versus RA, if you will. And questions?
Technically, RA is actually one possible thing you can do with RPC.
Okay, so that's a good question. You know, when you compare RPC, and let's just come to the comparison in a minute. Okay? Let's try to understand remote assignment first. Okay? And can you see some differences in the way remote assignment works in these three cases?
In datagram, the assignment may not actually happen.
Okay, so they may not happen. But there's actually something called reliable datagram, which seems like an oxymoron. But if there was a
reliable datagram, a datagram is like a UDP datagram. it's not reliable. And it's a TCP datagram, it's not a datagram, it's a packet and then it's a stream.
So why would somebody invent a term called reliable datagram?
That's more networky lingo. Datagram is just like a packet.
You want to reduce your overhead, so maybe you just want to keep retrying until they get it. TCP doesn't. Right?
So when you send a datagram, a stream, what are you sending, by the way? So let's think of streams now. What is the remote assignment? What's being assigned to what?
One block of data being assigned to a buffer.
Is it really in terms of blocks? Is a stream in terms of blocks?
Well, it's not. It's really just byte by byte or bit by
It's
bit.
really byte by byte. The port is really queuing things by bytes. Whereas
The application doesn't see that. The application sees blocks.
the application sees blocks. If I go and send 10 bytes, are you going to receive 10 bytes as an atomic unit?
No.
We've seen that in your example. In your
But
assignment.
the receiver doesn't know, but the receiver will see an incoming block of data.
The receiver will just
During a single receive call, it's going to see a block of data.
is going to see, maybe 1 byte, maybe 2 bytes, maybe n bytes. They're just going to, block means it has to be preserved. If I go and say my disk storage, okay, by the way, this byte versus block occurs in I/O, forget IPC, in operating systems. Okay, some devices are byte devices. What are examples of byte devices that understand bytes?
Like the Linux character devices?
So what are these? Keyboard?
Yeah, a keyboard.
A screen maybe, or the good old screen, teletype screen that used to occur in the ancient days,
Files,
right?
like that.
But whereas on the disk, the data are what? It's block. Use the block size. I mean, the block size is very intimately tied to the page size, and you do I/O in terms of blocks. You don't get 1.5 blocks. You get either 1 block or 2 blocks. Okay. Now, library routines on top can go in. When you're doing byte transfer, they can say, okay, by the way, we won't give you things byte by byte. We'll just give you a bunch of bytes together. Who knows how many? Okay. So that's just an issue of reducing the number of system calls. You say, here's a buffer. I want 1 or more bytes. Fill it up with as many bytes as you have, but we're not talking about dividing things in terms of bytes. Okay? We're just saying that I shouldn't have to make multiple calls to send bytes, and I should, because, making a system call is expensive. I shouldn't make multiple calls to retrieve it. So I'm just going to give you a bunch of variables and just fill them to a maximum level and just give me them all together rather than. Okay? Whereas a datagram, now I don't know how it, is. If you send 512 bytes, at the other end, can you get double the size or half the size, or will you get? I know it will fragment things. So if it's a network datagram, it will go as that unit actually, and there's no fragmentation and coalescing in datagram level, right? So it is so it is like your disk device. If I go and add reliability to it, then it becomes, and this was a term once used. I don't know whether it's still used or not. I tried to Google it once, and I don't think I found any choices there. But reliable datagram was basically a block communication. Yeah.
But logical-wise, even though it's reliable, the datagram is still technically,
Yes.
at that point, in terms of logic, you're still transporting the whole datagram as a whole, and it's time that happens as a whole,
Yes,
logically speaking.
that's what I'm saying. Logically speaking, if it gets there, you're doing a block transfer. You're not, and in fact, underneath, it's all block transfer, right? It's just that the socket layer is providing byte. Just as you can read bytes from a file, underneath it's all stored in blocks.
You're
Right.
speaking specifically to the physical.
Yeah.
Yeah.
So, but in terms of the API, it's saying, you know what? I'm guaranteeing you that there's at least 1 byte when you, I'm not keeping these boundaries.
What sort of protocol would you use reliable data?
I mean, you can just go and use the TCP/IP protocol if you want to.
But TCP/IP would send packets. So that's
Well,
my
yeah.
question. What's the difference between a packet and a reliable data?
So, this is a term that I heard used by guys, okay? It can be multiple packets. It can be fraction of, you're doing things at a higher level. So you can do whatever you feel like. I mean, if you think about it, serialized objects, serialized sockets are a general case of reliable datagrams. They're keeping track of boundaries. You can just use TCP/IP underneath and just say, okay, this is where my data ended, and some layer can receive from the TCP/IP layer into it. Or you can, these reliable datagram guys were really tying it to the network level. They're saying, let's not go and add this layer. We'll just have sequence numbers. We'll have all the stuff that TCP/IP has. We just won't have the socket paradigm of bytes.
And you shift it in blocks.
In fact, TCP/IP is not defined in terms of bytes, right? It's defined in terms of MTU, what's the message?
MTU size of the map header, that's that.
Yeah.
But that's at the physical level.
Yeah, so I'm just saying TCP/IP is not tied to the notion of bytes.
It's also tied to the notion of blocks.
So if TCP/IP was exposed a little bit more directly, maybe you'd have, but I know these networking guys talked about reliable datagrams at one time, long time ago. Okay. This is before object communication was there, just to go and have these blocks. And in your project, you've seen the need for it. Okay. So byte data communication, you're sending bytes, and basically the unit of buffering is in terms of bytes. And so okay. So I'm first saying typed versus untyped. This is untyped. There's some sequence of bytes is being sent, whether it's a block or a byte. That's next level of issue. Okay. So you're saying when the OS does communication, it just defines byte sequences, and it is some byte sequence, either one byte or some block, and it's assigned to a variable that can hold sequence. And byte communication, which is this, I really meant byte stream communication. Expression is a single byte. Byte blocks can be communicated through libraries, okay? And these blocks are not known to the port queue. So, I would say socket and IO stream are all sort of byte communication. And block communication is that you have some variable size byte sequence, and it's port queues in terms of byte blocks. And, if we could have a datagram of this kind, so datagram communication probably is this way. Okay. And then, of course, you can have object data communication. And if you're talking objects, you're talking of some language being around. And by the way, I just said this and I wanted to back off. So there's actually been an operating system developed that supported objects also at the OO level. And this was at CMU. It was done actually around the same time that Smalltalk was getting invented. And it was called COLA, I believe. And one of the guys, COLA. And one of the guys, before you type Snodgrass. SNODGRASS. So Snodgrass was a graduate from CMU who worked on this project, and he was a faculty member at UNC, in fact. So there's a tie to UNC. And when I was a graduate student in Wisconsin, and I actually went to Purdue first, I got a letter from Snodgrass, whose work I'd read, and said, come apply to UNC. I never heard of UNC. UNC was a graphics place at that time only. But so it's, I've got a little personal link to that. And then he left and went to Arizona or some other place. Very good guy. Okay. So there have been OO operating systems also. But typically today, people don't do that. People actually, provide objects only in a language. And Smalltalk, after Smalltalk, so Hydra was the operating system, I think, and Cola was the command language for Hydra. And so that was where the object-oriented stuff. And it was a capability-based system. And you guys heard of capability-based systems anywhere? Okay.
Security?
Yeah. And capabilities are in vogue. Capabilities are really tokens, if you will. Okay. So they're great. They're a great idea. Okay.
Did it work?
Capability-based?
No.
What should I say? Hydra, firstly the word Hydra. If you Google on Hydra.
It does have a Wikipedia page.
Which Hydra? The Hydra from CMU?
Yeah, an early capability-based microkernel designed to support a wide range of operating system services run on top of it. So,
and if you
object-oriented microkernel, which, what is it?
Yeah.
I was just going to say, people have played around with like microkernels and stuff. It seems like something always gets a little hairy. Yeah. Like,
don't be. Hey, don't.
Operating systems.
When I teach operating systems, my students build a microkernel, okay, and then they build something on top. So this is,
It just seems like one's never really broken out. Well, for a while there, I guess maybe Mac OS 10 had like, I think Mach was a microkernel, but I think they've centralized it more and more of the time.
Okay, so microkernel is one issue, O is another issue, capability-based issue is another issue. And let me just say this about capability-based systems. There was a talk. So last year we hired security people, right? We hired one security person. And how many of you were here last year? Okay. So did you guys go to the talks at all? Okay. So, there was this guy who came from Princeton, and he was doing hardware support for security of some kind. Okay. So he went and talked about the problem he had. And he said, look, I've invented this new architecture to solve this problem. And being an old timer and having done having studied the subject well, I think, I just said, wait a minute, capability-based systems can easily do this, and they have none of the they have all or, they subsume your architecture, and yeah, you're changing the architecture, so they do. So is there a reason not to use capability-based systems? And this guy, he looked like a baby to me. We all laughed. He was such a, and I was surprised he knew about capability-based systems. He said, yeah, they are a great idea, and I can't argue against them. So, did it work? Do things not work because the people who study them haven't learned them? So they don't know whether they work or don't work. So I think everything it had has practical values. There's always trade-offs. And I've seen, as things are going more and more towards objects, I think should support objects at the hardware level and have maybe capabilities. Having said that, the mother of all capability-based systems, the capability-based systems were just going in one direction till Intel said, we'll just do it right and we'll do everything. And that was the Intel 432, and it just didn't work. The architecture just didn't work, and that was designed for the Ada programming language. So, whether the Ada programming language got a bad name because of that or what. So, yes, in that sense, it didn't work. But that idea, like I'm telling you, the idea in its watered-down form was presented last year in a talk here. Okay. So, object-data communication. Assume expression is a location-independent object, and that means really that's serializable, right? So it's a variable that can hold such an object. So we assign object values to object variables, and that's pretty much what you do when you read something from an object string. And typically the port queue is in terms of bytes and not objects, and you have to sort of build some abstraction on top of it. Okay, and maybe yeah. Yeah, so actually, as I was saying this, I was thinking about my previous slides. That in fact, if underneath we are sending, these datagrams, then the queue in the router is in terms of datagrams, but in terms of the operating system, it might also be in terms of the network traffic. Okay, so just as this object communication is built on top of some. Queuing is different from what the user sees. I think in byte communication we can make the same argument. So in fact, I was thinking just exactly that when I was saying this, that even there the byte queue may not be, the port queue may not be bytes, it may actually be, and that's where the confusion arises in fact, because you get multiple bytes together. Okay? Okay, so now let us go and compare remote assignment versus remote procedure call. And if I give you an exam question, compare two abstractions. What kind of things do you look for in the comparison? I mean, what are the dimensions along which you compare things?
I would draw pictures and then see how the picture is different.
So you're saying you would go and, okay. So when you say compare is a very overloaded word. Okay? One compare just says, tell me the difference in semantics. And you would draw pictures so that you commit yourself to less. The less you commit to, the better it is. You know, it's almost like going to a court, right? Just don't say more than you need to. Okay? And you would draw pictures to describe the differences in semantics. Okay? And I've given you pictures. Okay? So I'm saying compare on based of quality. Not on how they work, but in terms of their effects. Okay? How do you choose one over the other? What are the so in general, it's the pros and cons, right? So there are multiple metrics. And some metrics are, of course, abstraction specific. But when I give you two system abstractions or two computer abstractions, whether you study them in theory classes or you study them in systems classes, when I give you two abstractions, what are some of the classic dimensions of comparison? Performance, okay? I mean, systems guy, algorithm guy is saying order of n, n log n. System guy is saying, 500 milliseconds, 700 milliseconds in these cases. No, I can't make general statements, but that's okay. My benchmarks show this, okay? If you're a database guy, you're saying benchmarks, right? So this performance is one thing. And then, of course, you can get into time and space and the trade-offs between the classic things.
The user requirements.
So how well does it meet the user requirements? So, when we're talking, okay, so you're saying what domains of applications each one is suitable for? Okay? And that could be a high-level question. You could say, look, it performs well when they're all on one computer and performs badly when they're on different computers. So the requirements are to have multiple processes talking together on one computer. Or that's, so that's, okay. And you're a software engineer, that's what you think. Other things?
I don't know how to make this more concrete, but it would be like level of abstraction almost, or like,
okay.
I guess that kind of comes back to unit of communication. But if you're able to think in objects, that's obviously higher level than, or a higher level of abstraction than thinking like variable by variable. So something along those lines.
So if I was to tell you compare Turing machines with linear bounded automata, you guys ever studied linear bounded automata?
Yes.
You did? Where did you study? Undergrad?
Yes.
Okay. I just somehow, I don't know why that came. Sorry? Yeah. But what is the hierarchy? Finite state automata, push-down automata, linear bounded automata. I studied my theory exams well before my PhD. I haven't seen that stuff since my PhD, guys. Before you guys were born. And then this, so you can. Yeah, but they do the same thing as Turing machines, regular Turing machines, right? No?
You'll get $1 million.
What?
I said if you prove it, you'll get $1 million.
You'll get a what? $1 million.
Yes.
Isn't non-deterministic just an issue of performance? That, when you say non-deterministic, I've not heard of non-deterministic Turing machines, but non-deterministic NP problems and probability problems, it's just a question of taking more time because you still have to verify the solution. So, Turing machines are as expressive okay. So, but what can be implemented on your computers? Actually, your computer is just a finite state automata, but because it doesn't have an infinite tape. But when you go and compare these, what are you doing? You're saying a linear bounded automata can be simulated by a Turing machine. A regular finite state machine can be simulated by a push-down automata. Okay, so the notion of expressibility becomes, which was the question we were getting to. Isn't this a special case of this? So, can you simulate one using the other? And that is the question you asked me. And I'm going to answer that and say, by the way, whenever you say comparison, think of simulation first. That is one more flexible? Is one more hard? Sometimes things are, one abstraction provides you with higher level programming, but it does fewer things by making some assumptions. Okay?
Is bandwidth requirement a reasonable basis for comparison?
Sorry?
Is bandwidth requirement a reasonable
Performance? you know, that's one kind of performance. It's not response time, but it is utilization. Okay, and not only utilize. You don't want to utilize too much, but we don't want to take more space, more time, and bandwidth will take more space in the router queues. It will go in. So in terms of just expressibility, can you simulate one with the other? Can I simulate remote procedure call, remote assignment, remote procedure call using remote assignment? No?
Not necessarily. It depends how you encode your message. Like maybe,
And depends on the procedure, most importantly.
No. So can I do arbitrary procedure calls?
Depends on your language, right? So if you can do something like monkey coding, you could send in your procedure as the expression, it sets a variable in a function, and that function's only job is to execute whatever code is passed as a parameter.
I mean, how is RMI built? RMI is built on top of sockets. Sockets are remote assignment. RMI is remote procedure call. Through one example, I've shown you can. Right?
Yeah, I mean, if you're able to pass numbers around, you can pretty much do anything.
that's all there is.
Yeah.
The thing is, there's probably like some kind of thread that's running on the server side. You send a message, it signals that thread to start this procedure and then return it using like stream that's set up. So I guess you could say they're both equivalent because you can simulate both using.
Okay, so let's just convince ourselves that we can do that. And you know, I spent a lot of time on this slide, so even though you guys have given me the answer, I'm going to torture you through it. So send expressions, encoding methods and parameters. Okay, so you send the data, you go and assign them to variables, and when they get assigned to variables, the side effect is that you invoke the method. Okay, and so okay, I can do it. So why provide why not just provide remote assignment when you can simulate one with the other? Well, you have to do some more work, right? Maybe I can write a library routine to do so. In fact, Sun RPC, which was one of the first practical RPC systems, was really a library to do that. Okay? So can you see why it should be provided by maybe the OS, if it could? I mean, it's not done through the OS, but can you see a reason for doing it at a lower layer, at the system OS level?
Putting what at the lower?
RPC at the lowest level. I can do it just through library routines, and that's what we do today.
Yeah.
I mean, your RMI is just a bunch of library routines built on top of the operating system.
I mean, I guess if you put it at the operating, well, I mean, you could maybe avoid like a network context switch or something. Like you put it low level enough, like switching into kernel mode, and then.
So how many calls did I have to make to the operating system to transfer my? If I transferred it all as one long string, maybe only one call. Okay, but if I'm sending, you know, okay, I'm sending the name, each parameter separately. I'm making maybe 4 calls. Then I make a receive call to receive the result back. Okay, this guy goes and makes a receive call to receive all of these, and then makes a send call. So you're making many more send calls, and OS calls are expensive. So when people were, you know, when people were doing simulations of one abstraction with the other, not RPC, they had many forms of send message passing, and one could simulate the other. The argument was typically that if you do it at the OS level, you make fewer system calls. Hence, the performance is much more. And this microkernel idea, it goes hand in hand with the idea of taking functionality outside the kernel and putting them in servers, and where you would normally make a system call to go and invoke some functionality, you send a message to another process. Okay? And if you are sending, if each system call is being replaced by 5 system calls, your OS functionality just goes down the tube. Okay? And I'm not saying this, I think, you know, when I was in Wisconsin, we guys built a very nice functional distributed operating system, and I mean, its performance was just so bad. You know, 20 milliseconds to send a message from one process to another process, regardless of whether you're on the same machine or another machine. Okay? Just because we just had, you know, there was all this stuff going on. Okay? So efficiency, several simulating calls or one simulated calls, less efficient if OS involved. Okay? If the OS is involved in, and then you could do things faster. Okay. And now, how would you simulate a remote assignment using remote procedure call? Just define a setter, right?
Yeah.
Okay, so define a special assign method, a setter method, a single formal parameter, and send the expression, send the value across. So will this be? How about the efficiency of this? If all I wanted to do was data communication assignment, and I was given RMI, I mean you've got both object streams and RMI. Should you be using RMI all the time, or maybe there is reason to have object communication? If what I want to do is an assignment, should I make a setter call? In your example, your favorite example, okay, your simulation, should you be sending the input string as an RMI call, or maybe send it as a string?
I mean, it's more efficient to send it as a string, right? And
Because
I mean, there's invariably going to be some overhead with making it a procedure call.
and there's marshalling, you know, there's all this stuff going on. When you want to do something, why use a heavier handler? Right. So efficiency, you know, RPC by definition is, especially the way things are designed today in the network, you know, it's less efficient. So there's pros and cons. So remote procedure call is great when requests must be serviced. Okay, and in your example, you're joining a session. Okay, so you're joining, you're giving a handle back, saying this is a callback thing. You're making a request. You're not just sending some data to be stored. Right? And simulation is awkward and not efficient. And when data must be sent, you know, like a command simulation, maybe remote assignment is the right thing to do. Okay? And remote assignment can implement RPC, however, simulation awkward and not as efficient. Okay, so that is why you have in Java both things. But in, you know, again, when religious wars were being fought, you know, it was one or the other. The question people said was one or the other. And you know, the idea there was, so in language design, this is system design. This is a real challenge. Do you just bloat it up and give this big, you know, Ada, Java-like language with all libraries, that you have a nice, skinny, simple language to understand, that you understand. And so people didn't want to go towards, you know, fat languages. Okay, so we've said we have remote assignment, we have remote procedure call. Okay, and when you're defining semantics, I mean, it's nice to define semantics in an object-oriented way, right? By saying, what are the exact operations? Again, I'm drawing pictures here. I'm saying, you know, a procedure call is going, resulting in being consumed. I've yet to go down under the covers and say, okay, what operations are being provided by the system exactly? And maybe we'll just use some syntax here to make that clear. So this arrow corresponds to what kind of operation? Or a send, and this is also, you're doing this request. So what do you do? You invoke or send. You can even call it send. Okay. So there is I mean, it's not as if the system is reading the sending process's mind and saying, okay, I'll go and invoke this call for you, send this data. Maybe there is some. I mean, I'm not discounting that possibility. Okay. I mean, you know, this is the age of automation and machine learning, and you know, why should I have to make a call? Just figure out I need to make this call, right? I mean, way back in the 60s or 70s, 80s, I don't know what, way back, even before my time. Okay, there was an instruction called DWIM. Anybody heard of DWIM? Do what I mean. Okay, not what I said. So you know, maybe that DWIM instruction is going to happen. You know, the Google Nows of this world, which will just volunteer information to you, you know, that you need. But, you know, in our current world, before this brave new world, we're assuming that somehow, you know, there has to be an explicit send of some kind. Okay? So, so you have maybe, you know, send port, comma, expression. Okay? Which port am I sending message to? And what is the value of expect? Okay? And in the case of my thing, maybe I'll call it send, or maybe I'll make it more explicit that it's a call. Okay? And what I'm saying here is that a particular port, and this is not entirely from my invention, people used to define one port for each service. Okay, so the file server would have one port, the print server would have one port, and to the file server you can send the request to open a file, close a file, seek a file, read a file. So you would say, okay, here is the port I'm targeting my communication to, here is the request name, and here are the parameters of the request. Okay? And then some languages said, no, this is too confusing. Why not just have a separate port for each request? And the collection of ports defines a service. You know, there was all this stuff. And assuming multiple, and sometimes I'm going to assume one port per method call, and I'm going to assume the other way around, okay, depending on the example. So every system will have a send operation in our world, and other operations can vary. Okay? And let me also just highlight the difference between language support and no language support, because these ideas came from both operating systems and programming languages. So the no language support was you say send port expression, call port method parameters. The trouble here is that, you know, that port could take values of different types. So then, you know, you'll have to make this very untyped. And people argued for typed ports. Okay, so this port is of this type, int port, and this is a double port of some kind. So you can only send values that are consistent with the port type. Okay, so ports were typed, and you could only send certain types of values. Okay, this is sort of an extension of socket communication, where you say, no, I'm not going to send an arbitrary object on this socket. I'm going to only send strings, or I'm only going to send some other kind of abstraction. Okay, and so you can send my load average, the load on my machine. A lot of these algorithms were load balancing algorithms. You know, processes were communicating, operating systems were communicating to make sure that this was in the context of a distributed operating system, where the idea is that when a new job comes in, it could go to any one of these various machines. So these machines were communicating their load averages, the loads, to go and find out which is the right machine for the next process. Again, this is a very complex algorithm system, solution, by the way. Huh? If you say we'll go to the least loaded machine, what's going to happen? If every machine says, you know, no, I don't want this job. And what is going to do? I mean, there was this thrashing. Okay, so I mean, this is a very rich field of load balancing. You know, how do you do it right? There's some kind of hysteresis built. Okay. So you can send to the echoer a string value. You can send to a load average port an integer, a double value. And again, here I can go and say, now I'm using your terminology. I can say send to port/method parameters. And now suddenly my send call becomes a lot like a procedure call, right? Where the port name is my procedure name. Okay? And I'm just doing a send rather than a call. You know, I mean, this is not my invention. This has all existed. In fact, most of it is in Ada right now, which is being used for defense. So this is not this, you know, and people love it who use Ada. I mean, at least those guys say they love it. Okay? And you can say send to add the add port 5 and 3. Okay, and this sort of makes it more clear that, you know, what's really going on. There's a service. Okay, send to the open call, send to the open port this particular document. Okay. So in this example, the signal signature is associated with the port, and procedure name is the port name. Okay, and that's, again, these are actual things. Okay, so the send is explicit. Clearly, the act of consuming a message is what we call receive. Does that have to be made explicitly? And what would it mean? Okay, so let's go and see what explicit receive might mean. In this case, explicit receive would be what kind? What format would it be? You'd say receive, port name.
Receive, port name, and the object which, in case of IRI, the method that's to be invoked is on a particular object. It could be a, just a standard procedure.
No, but just think here. What's going to happen to this 5 and 3? They're going to happen. What is going to happen to them?
As method parameters, they're going to be set as the input parameters to the method.
So my receive call would be what? If I have an explicit receive, you're not used to that from RMI. And RMI, there's no explicit receive. If I had an explicit receive, I would say receive, port name, add. And what would I have for 5?
One variable and another variable.
And so that becomes a lot like a procedure header declaration, right? And maybe you also have some return value. So you say port, formal parameters, and then some piece of code that has to be done. So you'd say receive int add, and this is literally not.
Piece of code is also sent through, or does a piece of code doesn't already exist at the server?
So this is the client, if you will. This is the server, and the server says. So this is interesting here. Huh? This is very subtle what's going on here, and this is exactly what Ada has. They call it accept. Okay. What am I saying? This is a statement. This is not a declaration. This is very important. So the process goes around, does some things, and then says, receive, at this point, I'm ready to receive. And if I get a message, then assign it to these values and execute this piece of code.
And that piece of code doesn't come from the client. That already exists at the server.
Yeah.
And that's kind of like.
Otherwise, the client could have done it itself, right? To some degree. You want it to be done some machine first.
Like in C#, you have delegates, like typed function pointers. I mean, you basically just say, all right, like if you have a 3 or a 2 argument thing there, it's in and returns in. So like that port, you could have a port of in, and it could be add, subtract, and you could find it.
But okay, that's good. But isn't RMI somewhat that way too? That you have these.
Yeah, I was just saying like that. I mean, that's kind of like.
But tell me, what's the difference between RMI and this? There's a very big difference between RMI and this. In RMI, you don't make a receive statement. I mean, in RMI, you just declare these methods. They get called. Here, the receiving thread or the receiving process makes this call. If that receiver doesn't make this call, your message is never honored. So what's the difference between RMI and this? No, which thread executes the call in the case of RMI? When you make a call, when a client makes a call on a server, what thread in the server executes the code?
There's a thread associated with each object because and that listens to calls made by clients.
So some non-application thread, some RMI thread. So servers also has its threads, which could be active at this time. And some system-created thread, which could be one thread shared by all RMI calls, or it could be a new thread created for each RMI call. We don't even know. Actually, I don't know. I mean, I knew at one time, but I've forgotten. Okay? And that thread can then interfere with my other threads here. And who knows what issues can arise there.
So that thread is kept separate, completely separate, sandboxed.
Whereas here, it is an application thread that executes it. There's no mystery as to what thread is being executed. So this kind of receive was meant for synchronization. And so that is the very big difference between RMI and this. Okay? And this is what Ada does. It calls it accept. And when you accept a call, at that point only it executes. And so this call is made as part of the receiving process's thread rather than some special thread.
So is this a good or a bad thing?
That's my question to you always, right? But and what are the trade-offs here? So it's always a good and bad thing.
Well, the programmer assumes more responsibility, but then is given a lot more power to do a lot of different things that you might not be able to do from RMI. But if you want to do very simple things, then RMI makes your life easier as a programmer.
So in the case of RMI, you think it's simpler? Because
those threads are managed by some higher power. You don't have to do it.
Okay, so that's a good point.
If you had some kind of like message selection thing, which I guess been received, and like you could have a bunch of messages in the mailbox, but maybe you could like pattern match on the messages.
Okay, very good.
Something like they could be built into the receive, and so you say, all right, well, I know I got X, Y, and Z, but I don't want X and Y, and I'll process those and send it back, and then Z is just somebody else.
And that's exactly what the examples all showed. Okay? The whole idea was, how do you do a producer-consumer problem using processes? Okay? And you would have guards, which we're going to get into soon. Guards, which are these Boolean expressions that come before the receive.
Okay.
And you just say, yes, a message has come to produce, but my buffer is full, so I will ignore it and keep the producer waiting till a message arrives from a consumer to consume it.
What's it? This is always really confusing. But what's the difference between a guard and a condition variable?
Okay, so we are going to solve that. We're going to address that problem so explicitly that you'll be very happy. You'll be probably more explicit than probably you might want. Okay, that's coming. Okay. Implicit receive. So have you seen implicit receive in procedure calls? This guy does a send. When they do a call, that's a send. It just happens. What has really happened? When you went and said, please go and register this object as a remote object, you're saying, please register each method as something that can be called when a matching send arrives. That's essentially what you've done. So can I imagine something similar here? Can you have implicit receives in the case of assignment?
It's pretty similar, right? There's some sort of thread that would just monitor, use each port. Each port is the variable, right?
No. We could do that, exactly. The thing is that in the previous slide, port was not a variable. I kind of confused things earlier because I was jumping onto here. You said receive port, comma, variable. And you said, the next receive, please use this variable.
Right.
And then you went in after again, subsequent receive, you gave me perhaps a different variable. But what I could do here is just register with the port a variable and say, next receive that comes, please go and assign to it. And I'm not going to make a receive call. Every receive that comes, let's just assign to this variable. And it's my job to go and empty the variable at appropriate times. Okay? So, system provides ways to automatically assign some known matching variable or call some known matching procedure when message arrives. That's what we're going to say. Okay? And you could register with port a variable. So you can say, okay, this is the variable that takes a new load average. Okay? And this is a particular method to call. And whenever an add request comes in, and essentially when you register an object, you're making this call for each method in that object.
That's kind of like the functional reactive programming that's going on now. It's like if you do mouse.xValue, it's like a special variable. That it's not like you get the x value of the mouse at one point. It continually updates. So if you do like mouse.x over 2, and you move the mouse, it like returns a function that will give you half the x position of the mouse like over time. So that's kind of.
But this is, So we haven't said what would happen when, two messages come in to the same variable. Is there some kind of interpolation going on, or here I'm assuming the last value got assigned.
I think it's only like one thing at a time, so it's like the x value of the mouse, so it's just continually
updates,
getting that, and sending it so that it's like it flows through the
so that's good. Actually, I guess that's a good example. I was going to ask you guys what's a good example for this, and it could be that I have a paint method that's going in and painting at some x and y position, and I'm just going to paint whenever I'm called. I'll just paint the last xy I received. I don't have to be told each time a new xy comes in. I like that actually. I don't know if that's what this is meant for.
Yeah, it's really cool. But because it auto propagates through the system, you don't have to write like an event loop or anything like that. It's all kind of under the code.
So that's okay.
That's sort of what.
So you just go and just present this variable, and when you need to read, and I said load average, that's another thing that whenever I'm doing rebalancing, I just go and see the load average I got from this pair machine, and at that point, I go and use it. And I don't have to go and do something each time, so I could do it. Okay? And one of the examples that, one of my Wisconsin professors, he was half AI, half systems, and half half languages, half operating system. I don't know, not all, half, one third. So he had this, you guys heard of alpha beta search? So alpha beta search, basic idea is you're doing some kind of tree search. And you're doing, let's say you're doing a chess program, and you're trying to look at all the tree of possibilities at that point. So there are some parts of the tree that you know are just bad. You don't want to go down that tree. So alpha, beta were two values that were constraining which part of the tree you went. And you always had some value of alpha and beta that could get refined later to more narrow values. So his algorithm was that, all the processes are just searching different parts of the trees, and they go and compute what they think are the best alpha beta values. And next time you go through the loop and you need alpha beta, you just read what you got last. And so if you didn't get the values, you would still do something that is not incorrect. But if you got later values, you would do a better search. Which is again, that I like the XY example, my load average example, yeah. So you can imagine this being useful. Okay, so I'm doing it pure theoretically right now. I'm just saying these are orthogonal issues. Let's go and see whether these things have meaningful applications. And we just thought of some. Okay. So reply. What does reply really mean in the two cases? So in the case of send, if the send is associated, in the case of a call, if the receiver is received with some procedure,
You want to
in that piece of code,
Well,
What do you mean by that?
I don't know. I'm trying to figure this out. Return value.
In remote procedure call,
Yeah. What would reply mean?
I mean, it's interesting if you, like, at the Java level, because you can have exceptions. So it's not just the return value of the method. You could possibly have some sort of exception that needs to beat the return value. But if you have a method that returns type up or type in, we'll say, then you can't return an illegal argument exception because that's a type object. So you can have.
So the question is it in remote procedure call, the simplest semantics are that instead of saying return, you say reply. Okay, that's easy to understand. That's what people did when they said reply. Okay, that they had receive, and they didn't do return, they said reply. Then you can get more interesting and say, okay, maybe I can reply more than once. And then how does that value get stored in the sender? I mean, it's a little tricky. Okay? So for now, we'll just assume in the remote procedure call, maybe it is the reply. You just return. It's a return. Does it make sense to have reply in case of remote assignment?
I mean, I guess the equals operator actually has a return value, right? You think about it.
Yeah.
I forget what it was, right hand side or something. I haven't worked with C in a long time, but
Yeah, because you can chain.
they get char as like a
Yeah, you can chain like an equals assignment.
Is it the right RHS? Is it the RHS
I
then?
believe it's already there, right?
Right.
It's either like int C equals get char, it's not null or something. Very
Yeah, you can
times
say
it's
if A equals B.
then it'll
Yeah,
be
yeah, that you said that in C a lot. If A equals
B.
B, if A equals B, and if B is a Boolean,
It'll just go if B is non-false.
yeah, or non-zero. And
Right.
C it's non-zero, non-one, right, or something like that. Yeah. So you're saying that okay, that makes sense then.
I mean,
Yeah, I like that. This is great. Yeah.
But if we're just doing sort of a remote assignment thing, maybe the only reply we really care about is whether that succeeded or not.
But that's
in a way,
that's an orthogonal issue, right? Reliable versus non-reliable communication. But here's the deal. How do you return a value? Is the value always going to be so in your semantics, whatever you assign will be the return value, right? Or you get some kind of exception. So does it even make sense to have a reply there? And no, what do you guys think?
I would still like to have one to know that it works.
Okay. So, you know, I had to worry about this thing, and because in the system I designed. So, you know, the thing is that this reply is not bound to any piece of code. It can occur anywhere. Because you receive a message, you receive another message, then you say reply. Who are you replying to? So I just say, okay, it is last sender is implicit port. And if there is a well-defined notion of what last means, okay, because there can be multiple senders. So it gets complicated, and that's my point here. But you could define, if you could define the last sender, then that is who you're replying to. Okay? But basically, reply belongs more here. Okay? So maybe things are not so orthogonal. Okay? Okay. So we finally understand semantics. Okay? Support access, semantics. Now let's get to the question that really started wars. Okay? If this started wars, this started even more wars. Okay, and the words synchronous and asynchronous, I mean, you know, is that the same as blocking versus non-blocking? And you hear of synchronous and asynchronous in so many contexts. In collaboration, it's synchronous collaboration, is it asynchronous collaboration? If it's synchronous collaboration, sometimes it means real-time collaboration. And then when you use the word real-time, people like Kevin and Jim jump and say, you know, that's not real-time. You know, it's very interesting, you know, Kevin laughs. Kevin came to this department, he was the first real-time guy. So the department was told, you know, everybody had to go and give their research areas. So Kevin said, real-time computing. And he said, okay, I'll be the only one. And almost every faculty member put herself in that group because they all thought they were doing fast computing. Fast means real-time. You know, all the graphics guys said, we're trying to render things in real time. You know, and no theorems are being proved. And so, you know, real-time, you know, has another thing. And then Microsoft guys, they did a user survey. And they said, should we call ourselves real-time RTC group? Real-time, which is what it was, real-time computing group. And then they realized that people like the word live better. So that's why you have live messaging, live meeting. Okay, so, but at least it's not, you know, real-time, not synchronous. Okay, so there's that world. Then in distributed computing, you talk of synchronous algorithms and asynchronous algorithms. Okay, and that's another world. Okay. But when you come to sort of operating systems and these kind of things, synchronous versus asynchronous has some meaning, right? So whenever you have an operation, be it send, okay, which is what we're talking about, or receive, or reply, which we'll get to, or be it some other operation involving multiple parties, okay, there's a device maybe, we talk of synchronous reads and asynchronous reads. We talk of synchronous sends and asynchronous sends. So is there some unifying definition that applies to these system calls that involve multiple parties? What does synchronous really mean? There are multiple parties. That's very key.
Just breaking down the word.
It just means everyone sees the same thing at the same time.
That's what the distributed computing guys do. When they talk about multiple parties, okay? Let's just talk two parties. Let's make our life easy. Okay? It's the CPU and the disk, it's the receiving process and the sending process. Let's not talk of group communication. Okay? So, in the case of send, it is one process, another process. In the case of read, it is the CPU, device. They can both operate in parallel. That's the key. And somehow this is tied to blocking and non-blocking, right?
Yeah, I would like, where do you split that up? Like, do you have is there such a thing as a synchronous non-blocking?
Okay, so maybe that's the same. So can I say synchronous means blocking and asynchronous means non-blocking? If I say that, you have...
No, that's what I was just thinking because I saw that they were in two different boxes on these slides, so I was like, well...
I'm going to look at them together, but to me, blocking and non-blocking is easy, right? That's too easy. I mean, you block or you don't block. But when you have two parties involved, blocking and non-blocking becomes an issue, right? When there's only one party, you've got to do the job. When it is two parties, you can say, okay, I've placed my order, and I can do something. I can not block for the order, or I can wait till my order is made. Okay, so there's somehow another party involved. Okay, so what if I said synchronous is blocking and asynchronous non-blocking? That could be a definition, but can you think of something has more semantics associated with it. Because blocking, I can block for 1 second, 2 seconds, I can block to various degrees. If it's blocking, I block until when? Let's put it this question.
Block till you're done.
Okay, now we're getting into meaning.
Yeah. Or into the specified timeout. Or
That is general blocking, okay? But when I get to synchronous, and I want to say synchronous has got some well-defined semantics also with it, I say, I am blocked till the operation I am invoking is done. And that done depends on the operation. I am asynchronous if I do not block until that time. I might still block 5 seconds, but that's not an asynchronous. That is not something that has meaning associated with it. Because I will write a different program based on whether my operation is synchronous or asynchronous. In one case, when I finish, I go to the next statement, I know my action has finished. There is some guarantee there. And that guarantee I will make use in the rest of the statements. When it's not synchronous, I may unblock before the operation is completed. So I have to be more tentative about what happened. That's the difference.
the question of interruptibility, does it also applies to synchronous? Doing synchronous just blocks until the operation is done or until it's interrupted by something external? Like the classic Java, you don't interrupt the exception.
No, the interrupter except, so that is, maybe.
Does that fall under the definition of synchronous?
See, that interrupt means I'm telling you this operation can't happen. It's not I'm interrupting you because I feel like doing it. I'm saying, you know what, you're waiting for this. I will tell you that it's not done. So you can still make, so people when they defined this, or when they were thinking of this, they weren't thinking of, they weren't thinking along these lines.
No, I'm asking that, sometimes other threads do, I'm interrupting you because I feel like it. Or because, I want you to stop waiting for it and do something else. Because the operation you requested, it doesn't have meaning or for whatever reason.
Okay, so if they're doing that, they're really not following the exception philosophy that Gosling said, which said that exceptions should be used only for exceptional events, not as a way of communicating between two procedures.
Not necessarily exceptions. What if a synchronous call, the wait that's associated with a synchronous call, that the wait that happens until the call is completed, what if that wait is interruptible? Is that then a true synchronous call?
No, if at the end of it you can't assume something
Right.
definite, either and what you should be able to assume at the end of the operation is either it can't be done. That's a strong assumption,
Right.
or it has been done. You can't have some in-between thing, maybe, maybe not.
That post condition needs to hold true if it's synchronous. In all of the cases, it's asynchronous.
In all the cases, asynchronous. Okay, that's the definition I'm going to give you.
So,
Okay, that was the classic definition. I'm not inventing this. This is what
so
people
if an
say.
operation will block until the operation, so if a call will block until the operation is completed, or if it gets interrupted by another thread, then that call is asynchronous.
Yes, if it gets interrupted before there's any guarantee.
If it's interruptible, I should say.
If it's interruptible, it's asynchronous.
It's asynchronous.
I would say that.
Okay.
Okay. So, operation invoker waits until the operation finishes. And I'm going to put the finish within quotes. That will decide for each operation what it means to finish. Okay? And finishing might mean I can't do also. And operation invoker does not wait until completion. So now going back to the question, is every synchronous call is blocking? But is every blocking call synchronous?
You block long.
Sorry?
You block long for whatever condition. So not necessarily.
Not necessarily. Okay. Okay. And by the way, when you're doing asynchronous, some other operation like a software interrupt needed to wait for result or completion status. Okay. You need to have something else. Okay. So synchronous versus asynchronous versus blocking operations. Blocking operation invoker waits. Unblocking possibly before, until, or after operation completion. So there's no guarantee when you unblock. You just blocked. And synchronous is always blocking. Blocking is not always synchronous. Okay? So, and this, I remember reading a CMU thesis actually. That was the first thesis where I saw that something that was blocking but not synchronous. Yeah, I can theoretically go and say, it is, you can block at times before that. But why would you block? Does it make sense to have an asynchronous blocking call? Yeah.
Isn't that exactly what he was getting at? Where
Time out.
Java, where you can be interrupted. So that's technically still asynchronous, right? Even though you are blocking until the conditions.
Until some. But
block is relinquished or something.
I'm talking. See, there's an operation. It's a different issue that you go and resume or wait, or here you are trying to do an operation like read or send. That is your main operation. And to block until something else, to be unblocked when time is. I can understand timeout, but to block to be unblocked when x is equal to 10, the x coordinate is 10 doesn't make sense, right? Yes, theoretically I could unblock when some other extraneous event occurs. But I'm waiting really, either I'm blocking, my job is to do this operation. So why am I thinking of x coordinates in a mouse position? So that example, yeah, theoretically is fine, but I don't know, what's a... So tell me. And where I'm making some call like this.
Yes.
So I'm reading from a file.
Okay. You're reading from a file. Or maybe you just sent a request to the server to do something, right?
Mm-hmm.
And I am running a separate thread, which is continuously taking input from, let's say, any analog device.
Okay.
All right.
And some condition.
Suddenly the user presses a button to
Abort it.
quit gracefully. And I would want to quit gracefully, in which case I would interrupt the procedure call that's happening, which may involve, in fact, this is actually something that I worked on, which I actually wanted to interrupt.
I would call that synchronous call, actually.
What?
I would call that synchronous because my program is making assumptions. Yes. The semantics of the program is, it's basically saying that call is over.
Yes.
In my mind, it's over. And that's why I said finishes within quotes. But, yeah.
So, on the previous slide, you said that, in blocking, it waits until it's finished. I think if you give us a broad enough definition of finished, then it's always synchronous.
Okay, so that, again, I'm saying that the meaning of the program, that somehow what I do after that statement is going to depend on the fact that I just got unblocked. But we actually saw this last time. Does it? And again, I hadn't thought of this till I saw this thesis. And in fact, it happens now in your sockets and your. So would you say that your pipe calls are synchronous? Writes to pipes are synchronous? Can you have more than one write pending? Is it blocking?
Yes, in streams of blocking.
So there's an example of non-synchronous calls that are blocking, and we kind of saw that last time, but we'll see it properly on Tuesday then.
But then you're just running into physical limitations.
So it's asynchronous. Semantically, I make no assumption after that, but it so happens that it's good for the OS to keep you blocked, to not let you release you.
So don't you think that should be called synchronous?
No, because my program doesn't know what happened in my program. When it unblocks, it can make no assumptions about what happened.
It has no idea. The program that's receiving from the pipe has no idea. It can't make any assumptions about what's been written to it.
Yeah, there's no guarantees after the send or that operation.
Yeah, but the program that's writing, the program that's sending the data, I can safely assume after the send call that whatever buffer I gave to the send function has been written to the underlying network layer.
So you can make some partial assumption, perhaps. Yeah.
Whether or not it actually goes
to
the physical layer
is
is a separate issue, but I can assume that it's written to the TCP.
Absolutely, absolutely. You can assume some, if it's not a direct buffer.
Yeah,
Yeah.
you can assume that, but that still doesn't get you much with respect to like synchronicity, because synchronicity, you need to make sure that whoever is receiving the message can be assured that they've received a whole message.
Okay, so which means that your definition of finished involves the message being received at the other end.
Yes. So before
the
the receiving end can start doing.
So let me. Okay. So maybe what I said earlier was not quite right, but let me give you the history behind this very quickly. When you said condition variables,
Post conditions.
no. When you talked about guards versus conditions, you were talking about monitors.
Yes.
Monitors and semaphores, we think in terms of synchronization. So this kind of IPC was used as a dual for that kind of synchronization. Okay? So yes, I was being a little more broad than I should have been perhaps by saying that nothing meaningful occurred when you got unblocked. Maybe something meaningful did occur, but the kind of stuff you're talking about does not help you simulate semaphores and monitors as this kind of synchronous calls I'm talking about. Okay? Because it involves the receiving process also. And
Sorry, could you repeat that?
we'll talk about that next time. Okay? When I talk of monitors and guards and everything, we'll see exactly why this synchronous, this kind of synchronous makes sense. Even though you're right that when you unblock, you can make some assumptions about what happened. You're right. Okay. So lights. So by the end of today, I will go and put the old exams, some old exams I have, to just give you an idea. But again, I've told you the 3 classes of questions I like to ask, and we'll see how far we can go. And please come early. Come 15 minutes early if you can. Can anybody not come 15 minutes early? Okay, come 15 minutes early. And in terms of what's covered, we'll finish IPC today. And that will summarize a lot of what you've studied before. So that seems like a logical point to stop for the exam. Okay? And the exams will not be cumulative. So it's not that you can forget what you learned in the first half for the second half, but the questions will not directly be on the first half. Any questions? Okay. So we were doing, we were looking at synchronous versus asynchronous. And we saw that was not the same as blocking. Synchronous was not the same as blocking. It's not equal to blocking. Synchronous implies blocking, but you can have blocking calls that we call it asynchronous. And the idea of synchronous and asynchronous operation goes beyond IPC. It applies to any operation. And the whole idea is that synchronous blocks, in synchronous you block until the operation completes, whatever complete means for a particular operation. Okay? So the question is, if you're not going to be synchronous and you're going to block, what are some good blocking times? Okay? So just as we have binding times, we can talk similarly about phases in the lifetime of a message and talk about till when are we blocking. Okay? And so we have to look at the communication pipeline, and we've seen this before, that you're sending an expression to a port. Either you're doing that in remote assignment, or you're actually making a call. And either way, you're sending some information that has to be first buffered in the system. So that's one logical point at which you could block until the message reaches there. So we're looking at the pipeline. So operation started. Okay. Then operation message in source system buffer. So it goes to your operating system buffer. Then it goes over the network and is buffered in the routers, and that's not our business. And then it goes to the system buffer in the destination computer. And finally it goes to some data structure in the process. Okay. So it either goes to a data structure or it causes a method to be invoked with some parameters. So it goes to a stack data structure. Okay. So these are the phases of a message, and you could block until any of these times. Okay, and synchronous operation means you block until either the method is finished or the variable has been assigned to the expression. Okay, so the question is, why might you want to block earlier than that? So we've gone through this argument a little bit before when we looked at sockets. Well, let's just recap for our exam. So why might you block until the message is in source system buffer?
Well, like in the case of NIO, you just care that it was sent and received, and that's it.
So in NIO, we don't block at all.
Right.
So that's okay. So firstly, why not block? Why not block at all? Okay, and that's NIO saying, hey, I got other things to do. Don't make me block. Right? I've placed my order, and I don't want to block till you cook it and you serve it and you get me water.
But that's on the sender's buffer. Like as soon as it's
So it's
the source's buffer, then it stops.
Okay, so that's good, because in NIO you can have the same buffer be used for both the application and the kernel, and maybe you actually block. So what happened in your NIO implementation? You guys went and put the message in some buffer, and that buffer was later read by NIO, and then it went and copied that buffer into its kernel buffer. Okay, so you put the message, you didn't block it all, and at some point it went and put it in. If it was not a direct buffer, then it put it into the kernel buffer. Could anything go wrong at that point?
Sure. So things can go wrong in that point, but none of those things are under control.
Sorry, they're not under our control. But what could go wrong, assuming the program is written correctly, assuming the operating system is written correctly? So these are all, you could have, the buffer could get full. So the reason you might want to block till it is in the system buffer is because, you want some guarantee there, right? So when I take my flight and I have to transfer flights, I have to, when you take an international flight, you have to go and put the box in near the conveyor belt. I just wait till they have actually put it on the conveyor belt, knowing that something could go wrong. It has gone wrong for me. So that's that kind of reliability you want. That look, at least it's reached some stage, the next stage, and at least I can go. Now things are not under my control. Okay. So and are there applications which wouldn't care about such guarantees? Yeah, it didn't. I just bought trash anyway, so the box gets lost, so what? There's the same kind of application that can use datagram. Right? So you don't need reliability, you're just sending video images, you're sending telepointer positions, one gets lost, another one will come around, so no problems. Okay. So blocking time, let's just go and see. Operation started. So what applications can afford to just, not worry at all? Okay. So this is no waiting, most concurrency without using extra thread. Okay. You can always, as we've seen, just have another thread that blocks. And I just gave, I'm sending load. The computers are doing some kind of load balancing, and they're sending each other load averages and saying, okay, I'm the least, I'm so much loaded, you're so much loaded, and we can figure out some algorithm to go and decide which computer will execute the next process. Okay. Message and source system buffer. So do you know of any system that, and so NIO is basically operation started. Okay, you don't block it all. And any system that blocks until the message is in source buffer that you know of? What other mechanisms do you know?
Wouldn't sockets do that?
Sockets, pipes. In pipes, you really do. In sockets, and pipes, if the buffer gets full, you just block. Okay, we saw that. And waits until buffer available and prevents flooding as a result. The nice thing is that you don't just flood the system with a lot of messages. Okay? And applications that could, make use of these semantics would want to, that, you've got data that you don't want to lose, but, your pipe application would be selling telepointers is what I've got here. I guess it's the same class as load average. I don't know why I put telepointer. I might just move it once. Okay, so I won't, I may not send a whole bunch of things. I guess that's what I'm saying here. Telepointer is a pointer that you're pointing at something and you're saying, and everybody else can see where you're pointing. Okay? So it's not your pointer but telepointer, and it's in the same class as load average that you send some. If you're dragging it, then there's a lot of events sent and you miss one. That's a big deal. But you do want the resting position. Whereas in load average, if load average doesn't go through, you'll have suboptimal solution, but you still have something at work.
So in that case, you would want a little more of a guarantee, but not necessarily like, it's 100% guaranteed.
Yeah, right. And that's a situation where you could flood. Okay. Whereas load average, you're not flooding. You're just, you're just sending it very apidly. Message and destinations buffer. Okay, so sender knows message did not get lost in network. At least there's that guarantee. And not only, it did not get lost, but there is some buffer available in the systems. So you want a little bit more guarantee. And I don't even know what application I have here. So I'm just saying sending load average on unreliable ports. So you're sending it, if you could block like that, you're saying, okay, I'm not going to, we don't know whether the message will go through or not, but I want to block till then, otherwise I'll do something else. Okay. And so now I'm saying that it's reached the application buffer. And is that useful to know? If you have TCP/IP, it'll get to the other's end. It doesn't mean that the process will go and receive that message. So this is a stronger guarantee than TCP/IP. And you're saying, look, I want to block till then, and if that doesn't happen, I'll take some alternative action. I don't want to just get it. Okay, so so you're worried that the queues may get full, and not only that the application. See, application also, depending on the kind of receive there is, the application is willing to receive my message. It's not that it reached the application buffer, it's the application got started. So if I'm, if I'm a server that's executing a lot of methods, I'm available to execute the next method now. I haven't gone into a loop, where I'm not available to okay. So you can give me your homework here, and then you can put it on mailbox, or you can know that I actually picked it up. Okay. And we guys sometimes, email tries to do that, right? Email does say that, okay, the message has been, there's some emails that let you do that, right? Confirmation. So here I've got an example that you want to just start an animation. You don't want to wait till the animation ends. So you know it started, and that's enough for you. Okay? The animation is going to take a long time to execute, and so you're just starting this. And then, of course, the ultimate synchronous thing. And, this is where, this is important stuff. Okay? And you know that you want to know that your file really got saved by Dropbox, and reservation made by airline. Okay. So we saw that our send semantics was a function of buffering, right? The message pipeline. The fact that there were all these buffers influenced, when we might wait until. Okay, so given a certain form of buffering, you may want to change your send semantics to sort of match it. Let's work the other way around. So given that we know there is a certain kind of send, can we do buffering more intelligently? And when we do buffering more intelligently, we want to do two things. We want to avoid buffers from being copied. Okay, copying is an expensive operation. And we want to avoid allocating too many buffers. So this is our, as system designer, that's our goal. So given that we want to ease, we want to make sure that these two decisions are made, the copying is not done and somehow the buffering requirements are low. If you want to do both of these things, we might choose semantics based on that. Rather than the application that I was talking about, we just can say that, this is implementation driven semantics. So which kind of asynchronous or synchronous, or does more blocking lead to easier buffer management and more efficient buffer management, or early blocking? So there's late blocking and early blocking, no blocking and synchronous, and then there's early and late blocking. So my buffer management in terms of efficiency and size, does that get easier with late blocking or early blocking? Early blocking will make buffer management easy? There's a 50% chance you'd be right.
In what case would late blocking?
Because I think. So why would I need too many buffers? Why can't I just have one buffer per process?
The buffer could overdo.
You mean no buffer doesn't? You mean the process could overdo?
The process could overdo.
But
I guess if you knew everything was going to block it every single time.
I mean, if it's synchronous, for instance, if it's synchronous, yeah.
And then you were just going to forget about it. You could just have one buffer. You would just kind of be responsible.
There's only one outstanding message.
I'm going to do this stuff, and then this is done. Like I don't care about that buffer anymore.
So the more you block, the less concurrency you have, right? So that's the flip side. But the fewer outstanding messages you can have. The fewer the outstanding messages, the fewer the buffers that have to be allocated by the OS. If you really want to make sure that things go through. Okay? In fact, the OS need not allocate any buffer. If the process is going to block till message reaches here, then we can keep the message in user buffer. And if the message doesn't go through, we can retransmit from that value. And once it's reached here, we can say, okay, we needn't now worry about it. And if it blocks after that, we use somebody else's buffer. So either we allocate one buffer per user process, or we just use the user's buffer itself, no copying. Right?
Could you do the other way around and have the user write to a specified buffer from the operating system?
That's what NIO allows you to do, even though it doesn't do any blocking. So that's dangerous. Because what can you do? You can have that kernel buffer, and then you can rewrite it before the kernel has gone and done anything with it. So it becomes dangerous.
Really? NIO does that? We write directly to the kernel buffer?
Yeah, there's a way to allocate direct.
Yeah, there's a way to do it.
There is a way to do it, but we didn't do it.
Well, I told you about it. You could have used it. But it's dangerous. Right? So that's what I'm saying here. Size of source and destination system buffers is an issue, as is copying. If sender waits, message can be kept in user buffer until it is in destination system buffer. Right? And there's no chance of flooding as a result. So we don't need a system buffer, is what my red line there is saying. Yeah.
Assuming the receiver's buffer is the same or bigger than.
Assuming that assuming that the receiver buffer, and that's what's going to happen. You're going to send messages, you're going to get an acknowledgement, and assuming there is space. Otherwise, you'll just keep retransmitting. Okay, so it seems that synchronous is more efficient, even though it may go and slow down the sender. It's more efficient, it seems. Can you see that actually asynchronous is there a reason why asynchronous could be more efficient also? We're talking purely throughput right now. We're not talking response time, you know. We're just saying, here, you know, we didn't copy things, so that was good. And of course, we didn't allocate too many buffers. But is it sometimes good to have outstanding messages?
I mean, it takes a lot to do something. You should probably be doing something else instead
So
of
that's the application.
sitting on those resources.
So
Yeah.
surely, the application could do something else.
Right.
So the response time of the application could go faster, could be smaller, if there was asynchronous operation, right? Assuming we're not using threads. But from a throughput point of view, can more messages per unit time be sent if it's asynchronous? Think of the unit of transfer in sockets and NIO. What is the unit of transfer? Unit of send and receive. Byte. Do you really want to block after every byte? Do you really want to wait for the byte to go across and then the next byte to go across and the next byte to go across? Right? You want to go and coalesce messages into sort of a network frame. Or maybe even coalesce multiple. You want to send as big a chunk of data as possible. I mean, that's why, you know, some of these I/O operations, read and write operations, are asynchronous. We don't want to write to the disk on each byte. We want to go and just write it into system buffers, and if the power goes off, as I said, you know, they'll be hopefully written onto disk. So that's the other flip side. So you can't coalesce multiple messages into one network message, and so that's where you lose a little bit. Okay, and coalescing is more important than byte communication. Okay. So typically, byte communication mechanisms don't, as a result, make the sender wait until the message is in, data is in source, in the destination system buffer. Okay. Okay, and even if and because of this coalescing, there's an operation that you'll see in sockets and NIO, which is flush. Okay, that send the data across. Otherwise, you know, because you do really want at this point, don't want it to wait too long. Okay, did you use it in your sockets NIO? Okay, yeah. Okay. And if you're using sender buffer, you know, async NIO does have direct buffers. So what do you do in NIO then? If you want to use direct buffers, what should you be doing if you're going to program, if you want safe programs and you want to use direct buffers? So how do we know? How do we get to know that the buffer is available? Select. What does select? What kind of notifications does select give you? You know, new data have arrived, or I have actually written your data. That was one of the write-op, right? Read-op, write-op. So I've written and so that is some indication that, okay, the buffer is free. So you get the signal when it's, you know that the previous write has finished, right? So you know that the previous write is finished and it's now going to execute your current write. So in that sense, you're not too happy here.
So you're saying you do one write and then remove that from your pending writes, and then so you alternate per message as opposed to trying to output all your outstanding messages at once.
Yeah. So you got your, you go and queue your buffers, right? And then, the system may not be immediately ready to go and write them. So it'll go and give you in the select call, it'll tell you, okay, I'm ready to write. And it'll go and remove the buffer, and you can then, and when you get, and so at that point, if you listen to the event, you can go and know that the previous buffers have been written. Okay, and those are available now. So that select call is essentially a way of telling you that It's saying, look, I'm ready to do the next write, which means the previous write must have finished.
So NIO gives you that guarantee.
It gives you that signaling capability. You have to go and block on that. Okay, you have to do blocking at some point to get that. Okay. So can you select to determine when it was available? Okay. So we have, we looked at the synchronous versus asynchronous semantics for sends. Now let's look at the synchronous versus asynchronous semantics for receive. So for sends, one can imagine things being synchronous or asynchronous. Does it make sense to have receive asynchronous? I mean, there's very few systems, if any, that have asynchronous receive. What would that mean, and why would you have it?
I don't know, discount, but you have things that'll give back future. So they immediately return, but they return something that
It's going to be valid in the
that
future.
just represent that there's this ongoing thing that may or may not block when you get it back. So it's kind of like defers.
So,
But not necessarily. You have REC from.
sorry?
You have received from in unreliable sockets, in UTP sockets. So that isn't blocked. But it says that there's nothing to read.
Yeah, it's a polling read.
Yeah.
It's not polling. This is saying that, look, I'm just not. That's a very, very important point. So in Xenu, there is receive clear, okay, which is the same thing. It says, do I have a word right now? If not, return. If give this one. So polling is different from this future thing, saying, I'm willing to receive, but I'm not willing to wait for the receive, and the receive can happen later in the future. That's the point. And when it happens, please go and assign to this variable. When it happens, please execute this procedure. So, asynchronous receive, does that make sense? For RPC, does that make sense? More, perhaps?
I mean, if your application will tolerate it, maybe your application says, I don't care when I receive, but when I receive it, I'll process it.
Yeah, that's what happens in RMI, right?
Right, and it's a matter of a callback.
Yeah, it's just a method that's called, and there is no single thread there. So it's almost like implicit receive there. That you're saying, hey, I'm not doing explicit receive, just whenever it's available, in some thread executed. Here you're saying something very similar, and you're actually, you're giving actually a variable and saying, use this variable for the next receive, and for the next subsequent receive, you might have another variable. So you're just basically saying, I don't want to block, but when it does happen, do this action, and then maybe give me some kind of interrupt, or give me some way of knowing when this happened. Okay, and I could have a select call to do something like this too. Okay, so synchronous operation invoker waits until the operation finishes. Synchronous receive blocks until remote assignment or procedure call finishes. That's synchronous receive. For that, asynchronous operation initiates operation. Process. Operation invoker initiates operation and does not wait until completion. Okay, but it may happen after that. So it provides buffers to receive expression or method call. It provides a way to gather the data. Okay. And some other operation needed to wait for result or completion status necessary. Okay, so let's just be clear. The difference between implicit and asynchronous receive, they're very similar. In implicit, I went and registered. I went and said, okay, whenever a receive occurs, use this variable for it. Yeah, register this procedure. So you do it once at the beginning, and that's it. In the case of receive, till you've done the receive, or till you've done that message will not be received. You're saying at this point I'm ready to receive, but I don't want to block. Okay, and different buffers may be used for different. In the case of assignment, different buffers may be used for different variables. Different variables may be available, used for different expressions. So the first receive that comes in will go to one variable, the next one will go to another variable. So it's not as if the same variable is being used again and again. Okay, even though the idea is very similar. In case of procedure call, it's basically the same thing, except that the procedure will not be executed till you've indicated that you're willing to receive Okay. So here, the answer is quite clear, much clearer. That I've said, here's a variable, and whenever a receive occurs, you assign to this variable.
Right.
Okay, and you will do that at the beginning of the program. Okay, typically before you're doing anything else, this is registration.
Okay.
With receive, you will say receive once, receive second, receive third time on the same port, which would indicate that that the next three receives should be using these three variables. So you can give different variables for different receives. Okay, until the first receive occurs, it's not, you're not starting the operation. Okay? And here there's very little difference, except that again, till you've done the receive, the procedure cannot be executed, which is also true somewhat for register. Okay, but doing multiple receives doesn't make much sense. Okay, so the asynchronous receive is just not done very much. So it's hard for me to go and point out at this system and that system. Okay, it has been done, but I'm just saying not much. Okay, nobody's tried to do an asynchronous receive here because that's just implicit receive. But that people have done. Okay. So in an asynchronous receive, a special call made for each receive message. Okay, so that might mean here that if I do one receive, I can only have one outstanding method call. I can have one method call, and till I do the next receive, the second call will not be executed. I think that is what we will interpret this as. You have to do multiple times this receive, once for each call. Whereas registration is done once for all possible things. So that is how I would define it. Okay? So that essentially when you do a receive, you're allocating a stack frame, let's say. And that stack frame will not be reused for other calls. And there might be some application that might want to make use of this. Okay, so we have send times and blocking times, the send and receive blocking times. And there are many operations. So connect, socket.connect blocks until, I think, did we go through this last time? Maybe not. So socket.connect waits until the other party connects, and accept works until, so this is basically a rendezvous going on here. The server socket waits, blocks until the matching connect happens, the connect blocks until the matching accept happens. So they both finish at the same time. Okay, so that's the blocking time here. So here actually this is not the same time. You block until the next client tries to contact the server socket. So as soon as the message is received from the client, it unblocks. And when the message reaches back the client, we unblock him. Right? And block until the system buffer, that is what we do essentially with writes. Okay? And in the case of my animations are off here. In the case of reads, we block until a certain number of bytes, until non-zero bytes are received. Okay? So this is just showing you that how the blocking time decision can be made differently for different operations in sockets. Okay, so I mean, trying to combine RPC and assignment, and maybe some of these things don't combine very well, even though we've defined some semantics for them. So does it make sense to have, we talked about asynchronous receive in RPC. Does it make sense to have asynchronous send in RPC? RMI doesn't do that. RMI makes you block until the method is finished. Does it have a clear meaning, asynchronous RPC?
What would that look like for the receive?
So for receive, let's just talk of send first. Okay? That's easier to deal with. It's receive, it just means that, look, I'm available to execute. But let's just talk of send. You could always have blocking receive and unblocking sends, right? That's what happens to some degree in sockets. You receive blocks until you get more than 1 byte. More than 0 bytes. and send doesn't block at all. So what would it mean to go and not block for procedure call?
You're not waiting on the return, or
So you're not waiting. So for void method, there is some semantics possible. You just send the request and say,
Fire and forget.
yeah.
Once it happens,
In your application, would that have been fine? You're just sending the message across and say, okay, whenever it gets, as long as it gets there. I don't need to wait until everybody's seen it. Maybe you need to give that feedback. Now, when it's a function call, it becomes trickier. Okay? So maybe you'll block, maybe you have some software interrupt to go and get the result back, or maybe in that case you unblock. Okay? And in fact, do you know of any system that does it? So,
somebody has a cloud storage method where the cheapest level of retrieval is actually a sneaker network.
a what network?
It's a sneaker network. It's, you request the data and it'll get back to you eventually because we have to walk across to the storage facility and get the tape and bring it back.
So you just get back a notification,
Yeah.
right? So that's an application that could make use of this, as could your application. And in fact, this is now in vogue. I mean, this is Google's RPC, and their built-in RPC system is non-blocking. Okay, so you guys should look at GWT, and it's built on top of a Google's RPC mechanism, and that's pure. That's even the so Gypsy, the system I'm going to show you next, has blocking for procedure calls, function calls, and no blocking for procedure for. So blocking for function calls and not blocking for procedure calls, whereas Google just has absolutely non-blocking. So starting remote thread. The basic idea is that think of remote process invocation versus remote procedure call. Remote procedure call is a blocking call. Think of that logically. And think of remote process call as being a non-blocking call. So what you're really doing is starting a remote process without waiting for it to finish. That's what it logically is, if you think about it. We do that inside one computer, so we can imagine doing it across computers also. Okay. So you're starting a remote animation, for example. Okay, you're just starting it, and you don't need to block until it finishes. Okay, so the typical thing is in procedure call is that your send is synchronous, your receive is synchronous also. Okay, which means the following: that the receiver can make the sender wait. Okay, because we know this operation will complete when the receiver finishes execution. Okay, and the message result is received. The result is received back. Okay, so the receiver can make the sender wait. The sender can make the receiver wait. The receiver is waiting till the message comes. Okay? And at some point, both the sender and receiver are waiting at the same time. There's some phase there where they're both blocked. And that phase is called, it's got a technical term for it, and I've used it earlier in the class. What might you call it? When both processes are blocked together. No, this is not deadlock. Deadlock is deadlock is deadly embrace. That's what they call it in Europe, where you can't make progress ever.
Association?
I'm just asking. Yeah, it's the colorful word for it is rendezvous. Okay, and this was invented in the context of ADA, so this is called the ADA rendezvous. Okay, so you are waiting. The sender is waiting until the receiver is ready. Receiver code executed, so they're waiting. So this is the rendezvous. And then, okay, and I'm talking here that here the receiver made the sender wait, here the sender made the receiver wait. Okay, and this is running. Okay. Okay. So let's look at synchronous versus asynchronous receive. So we've understood, synchrony at the send end, with send and with receive. Okay, so all of these could be synchronous or asynchronous. Okay. So why might you have an asynchronous receive, by the way? We talked to semantics, and people don't do it very often. But yet I mentioned it, they must have some application. So what is some advantage of having an asynchronous receive? Why might you not want the receiver to wait?
I mean, if you're expecting that all of your functions you call are very computationally intensive. Maybe, so I guess from my experience, something that you use with like machine learning, you spin off a bunch of like generations of models. Later on, you can list them together by joining them. But you don't necessarily want to wait for the actual model creation to finish to be developing well.
So you don't want to wait, same thing with send, right? We said send, we don't want to block because we have other things to do, right? Receiver, we don't want to block because we have other things to do. With send, we will unblock at some point, right? As long as the message gets through, or we'll time out. With receive, in typical applications, are we guaranteed to unblock? If I'm a server, and no one sends me a message, and I have other things. So supposing I'm a server, I can go and service the open port, or the request on the open port, a request on the close port, a request on the seek port. If I'm blocked on the open port and nobody opens, I can't go and block I can't go and service the requests that come in on the close port. Well, I could fork multiple threads, but then maybe there's all kind of synchronization problems that arise from multiple threads. Maybe that will be an issue. So in that case, I could just post a receive and say, I'm going to receive from any of these things. Okay, so I receive on this, and this, and then maybe I can do a little wait afterwards. Okay, so that was the motivation for asynchronous receive when it was. Okay. With synchronous, you don't need to have a separate operation to determine when operation finishes. And sometimes receiver does not need notifications, especially like a shared memory. They're sharing some memory. I talked about alpha beta surge. And the trouble with the synchronous receive is that the receiver can block on a port on which a message does not arrive. Okay, and you can't do something else. If all you're doing is servicing that port, no issue. Okay. So can you guys imagine that we do want synchronous receive, we don't want asynchronous receive, okay, for various reasons. That we want, we want only one outstanding message at one time. And how could we have the ability to receive from multiple ports and yet be blocking? So we want synchronous receive, and yet we want to service multiple requests. And
you already mentioned that, you need separate threads, and then
you can have multiple threads, but then I'm doing things concurrently. I want to do things sequentially. So what do I want? What's it going to look like? I have receive port, right now. It's either synchronous or asynchronous. I can say receive port, receive port, receive port, and then do wait. Where I get to be told, this particular message. With each receive, I get back an ID, and in the wait, I get back which ID. Was which transaction finished, which basically ID is the transaction. So I want receive, I want synchrony, and yet I want multiple I want to block in one thread, no wait afterwards. I can add a new construct. Think of programming language. I've got send, receive. I can have some syntactic sugar. Think of the switch statement.
There's some sense in which you want to like monitor the various receives you're currently in, and then just sort of switch in between until you have something ready to receive, right?
So in switch, yeah, so you want to basically have a switch. It is a switch in the sense that it has multiple arms, right? That's what a switch has, right? So the arms in this kind of funny kind of switch will be what? Receives, right? And then the semantics will be, so waiting on multiple receipts. So you got either receive port 1, receive port receive of this kind or receive of this kind, and a single thread process can expect messages on multiple ports. So you can fork a different thread, but that leads to all these issues. And what we want is a new construct for single thread and sync leave, and we'll have something like this. Okay, select, receive. Whether it's assignment or procedure call, I'm leaving that undefined here. That's what my dots are. And this what would be, I've got the syntax now, tell me the semantics. We've kind of hinted the semantics, but what might the semantics be here?
Well, wouldn't at the top of this switch, wouldn't you have to designate that you want to listen to all these ports, and then when you receive the received message as some form of identifier to say, on this received?
Okay, but that's the thing, right? What happens with the case statement?
Right.
You see, you have, that particular arm is executed.
Right.
So you don't need an ID now. You don't have to go and mess around with, okay, I posted a bunch of receives, now I'm going to do a wait, and I get the ID, and if ID, and then I'll have to have a little switch statement, right? If ID is equal to this, do this. If ID is equal to do this. Rather than using a conventional switch and this kind of mechanism, I have a different kind of switch into which receive is built in. So we'll call it select. Select is only used for receives, not for, this is not, okay? It's not as if this is a switch statement. This is a special kind of select whose arms are always receives. And if it's a remote assignment, that assignment happens. Or if it's a procedure call, it will be that method being executed. Okay? So my select statement is synchronous or asynchronous? These things are going to be synchronous. We want synchronous receives, right? So my select statement will?
Asynchronous.
Well, do I block? Okay, firstly, do I block or don't I block? Maybe that's an easier question.
Well, you would have to.
You would block until?
You get something.
Until some message arrives. Okay?
Yeah, isn't it just like a while loop, like switch statement?
There's no loop here, firstly. There's no
Yeah,
loop.
but like under the scenes, don't you have to do that?
Switch is check if first condition is true, or second switch. The switch is not a blocking statement.
Right.
This is a blocking statement.
He's saying we're defining something that's similar to a switch, but it blocks.
And its arms only include receives.
Right.
Actually, they've tried to have both sends and receives, and it just causes all kinds of semantic issues. Okay?
So it's like a pattern match on a
So we'll get to pattern match, but right now it just says select, and select until one of these receives, until some receive can unblock.
okay.
My receives are blocking. We know when they'll block or unblock, and it depends on whether it's assignment or procedure call. So I'm blocking until, I'll unblock when one of them can unblock, at least one of them. Then I unblock. Okay. And this is a statement. So the question becomes, when I come to the statement, if there's more than one arm that's enabled, which one should I execute?
There's no rules. I mean, depends on what's convenient.
So, but I'm a language.
Maybe precedence order, top to bottom.
Okay, that's
That's like how the pattern matching works in most languages, isn't it? And then at the bottom one is like your falter, just like a switch.
so. If I go and say import in Java, import package p.c, and then I say import package p2.c. Okay. Does the import order matter? Is it that my first import will get precedence over the second one? Or is that an error? So sometimes order matters in programming languages, sometimes it doesn't matter.
I mean, I know for C, like with the defines and stuff, like you can start.
Yeah, that's.
Stuff, I think
But that's
Java,
that's statements.
It's like it has a multi-phase compiler, so it'll error out if you have a name comp.
So it just says a set, right?
Yeah.
So sometimes order matters, sometimes order doesn't matter. And statements, order does matter. But declarations, we don't know. Okay, and this is not that you're saying one after the other. These are sort of equal. In switch, of course, you go from top to bottom.
Right.
So people had all kinds of semantics. First one is order can matter. And this stuff was done in Ada. And Ada was a very, written for reliable programs, and that's why it's still used in the military. And so the answer could be first one, it could be last one, it could be random. What else could it be?
You could prioritize them.
Based on? So you could sort of just give some numbers, 1, 2, 3, 4, 5, 6, or so the first message that came in, that seems like a fair. I've seen that semantics also. Okay, because the messages came in some order, and after that the select statement got executed. So you go and service the first one, that will prevent starvation. None of these are semantics that people settled on. You just tell the programmer, you can assume nothing. We'll do whatever we feel like. We might do fair, we might do first, and such a solution is called non-deterministic. So that the programmer can make no assumptions about the order, and the program should just work regardless of which one is serviced first. Okay? So that's what Ada settled on. So select operation waits until a matching send arrives for one of the receives. So that is why it's sort of like a pattern match thing. And it completes when the receive completes. Okay? So what happens to the other receives then? I serviced one non-deterministically. What about the other ones now?
Well, as soon as you're done with that one receive, you go back to the select and process the next one.
So more than one matching send, pick deterministically, and this is how it normally goes. Okay. That's this is a lot of languages had this kind of stuff. Okay. Okay. You kept talking of pattern matching. What were you thinking when you were saying pattern matching? Sure, the message matches this particular port, on that port. But could you imagine something more sophisticated also? So right now when a message comes in, it says whether the message has this port or not. Basically, right?
Yeah.
So to that extent, there is pattern matching. Can you imagine something more sophisticated also? Multiple? Okay, so it could depend on the type of the message. Match on sender, could match on some condition. So can we then, and I used this term last time, what's the term I used for some Boolean condition being attached to a receive? And at that point, Asad said, how's this like, isn't that a condition where in a monitor? I used a term. Okay. So I can attach with each receive a guard. Okay. And that guard can involve just global variables in the process, Or it can, some people have talked about using the content of the message, being able to peek into the message, and based on the message contents, decide to receive it or not. And that cannot be supported by this syntax. Okay, that's just some complex stuff. But there was a PhD that did that also. Okay, so I can attach a Boolean expression to it, and now my conditions would be, forget about why this is useful. Now I will execute, when I come here, what is the condition for my being able to execute a receive? There should be a message, pending message that matches that receive, and my expression should be true. Okay, this is how I'll build precedencing. If I really want precedence, I can impose an ordering with that. Yes. Now, why would anybody want this, by the way? Okay, I can do precedence. Can I do some famous problem this way that you all have heard of? Can I do some famous problems? So what are the famous problems you guys learn in OS?
Scheduling.
Sorry? Scheduling. But that's a sorry, Danning philosophers. Okay, but before you program Danning philosophers, what are some easier programs that you tend to program? Producer consumer bounded buffer. How could I do a bounded buffer using this? What's the semantics of bounded buffer? That if my buffer is empty, condition. Okay? If my buffer is empty, the consumer should wait. If the buffer is full, the producer should wait. Right? So, how does that relate to this? So you have a producing process, a consuming process, and you have some bounded buffer, right? So what would this be? Producer process, consuming process, or some other process?
Wouldn't this be the consumer because it's waiting for something?
But we want the producer to also wait, right? So then, if it's both, it's neither producer or consumer. And it would be what process then? So if you have monitors, you have a producer process, a consumer process, and then you have a monitor that encompasses the bounded buffer. The monitor makes you wait, makes the producer wait and consumer wait. So it is the manager of the bounded buffer that's making the producers and consumers wait. So this piece of code would be executed in the manager of the bounded buffer process. Right? So my get would be correspond to what? Here? There's get input, right? What will get input correspond to here? Somehow these conditions are corresponding to the buffer being full or the buffer being empty. So my get input would be separate ports. I'll be doing receive on get, receive on put. And my receive on get and receive on put will not be always allowed. My sender will go and try to do a send on get, send on put. My consumer will do a send on get, but they'll block until the appropriate arm is enabled. Okay, and I'll show you code to make this easier. Okay, so receive is matched if a matching send arrives and the guard evaluates it true. And use basically is supporting preconditions. Okay, you're saying, look, I don't want to execute this stuff till its precondition is true. And rather than just saying, okay, I'm going to throw an exception, I'll say I'll make the sender wait until my precondition becomes true. So this is an interesting kind of precondition where it can cause blocking to happen because it may later become true. Okay, and here's my bounded buffer thread process. So where my bounded buffer was in a monitor, now it is in a thread, a bounded buffer thread or process. And what's it doing? It's saying, okay, loop, select, when size is less than max size. Okay, that's my syntax for the guard. Okay, then I'll receive the put. When size is greater than 0, I'll receive the get. And this is just my get input methods done through receive syntax. Okay? And each time I do a put, I allow, so I'm executing this statement multiple times. And so that's a difference between registration and receives. Okay? And now I'm just doing the regular stuff that happens in bounded buffers. I've got a next in, next out. I'm incrementing the size when I produce. I'm decrementing the size when I consume. I'm moving the pointers. And that's my bounded buffer. Okay? So that's yet another way to do bounded buffer. Okay? And that was, this was the classic problem that was used to do. That was used to motivate this construct. Okay? So the producer says send, put hello, and the consumer says send, get. Okay? So that's the kind of semantics you basically have. I'm sending to the get port, I'm sending to the put port. Okay? So what's important there is that you had one thread that sequentially went through and executed the receives. This is very important. Only one arm was executed at any one time. That is like having an entry procedure in a monitor. Only one entry procedure in a monitor, only one synchronized method in a Java object executes at any one time. Only one receive executes at any one time. And that's much easier thing to deal with than what happens in RMI if you don't use monitors, where you get all these requests and they executed perhaps concurrently, and the synchronization becomes an issue. Okay? Here things are much more organized. That's why data is still used for military. Okay? And where you want more reliability. And where in monitors you have the conditions, now you have guards. Okay? So in Java you can do wait and notify. Okay? Those are basically conditions. Okay? Here you have guards. And I'm showing you right now a Java execution, a Java monitor, and this ADA process in Java syntax. Okay. So here I have synchronized method. There I have something executed in an arm of a loop. Okay. And there I, here you sort of signal. Actually, this is not quite Java. This is sort of Mesa actually, which is a sort of more elaborate form of Java. But what I'm doing is I'm saying, so you guys have heard of monitors, right? And I know you guys who did undergrad here have. How many of you haven't? I'm just curious. You haven't? So I have some stuff. Just Google on monitors. Okay, that would be important. But in monitors, you have conditions which you can signal, and which you can. And so what I'm saying here is actually, in Java you can say proceed all. Okay, that's when you broadcast on a condition, and or you can say proceed. Is it called proceed all? Is it called proceed all? No, what's it called in? Notify all. Notify all. I'm sorry. Notify all. That is what my condition broadcast is, and there's just notify, which is my my signal is just notify, and then wait is just the wait in Java. Okay, and so this I'm using a different syntax here, but this is basically so with conditions you can go and wait on on some sort of like semaphore as a condition that somebody else can signal on. And so let me just draw the duality here. You have entry procedures, these synchronized methods, and they correspond to receive statements. Okay, that's what I'm showing there. The idea of having a loop in which you execute one thing at a time corresponds to having entry procedure. So receive corresponds to a procedure here. Having a loop that goes and does only one at a time is like having synchronized methods. Okay. And my condition wait. So when I do a wait here, that corresponds there too. Yeah. that corresponds on the left too?
Just don't receive.
No.
You're waiting on something?
Yeah, when you're waiting here, what are you doing there? You're waiting on a condition to happen, essentially. And what's the condition there?
So do you just check the guard? Do you move on? Or do you...
Yeah, it's the guard. It's the guard. The guard makes you block there. This guard is an expression there. Here you have to go and bury that. You have to say when, condition, then wait. Okay, so it's a little lower level. Okay, this is a statement that says while, and you guys, there's hint semantics and there's non-hint semantics. That's why I've got a while loop there. So I guess, without knowing what monitors, this is not totally going to be appreciated. Okay, but in monitors, you have this notion that when you unblock, you're not guaranteed some condition will be true. So you have to go and do things in a while loop. So where I do when, condition, wait, that is all clubbed together into that particular guard condition. Okay. And when you do signal, when you go and signal there, that is like returning from a procedure. Because whenever you return from a procedure, then the next condition can be evaluated. So that's return from RPC receive. Okay. So this is there used to be a big debate between message passing and procedure call. People were talking about how operating systems should be designed, and people had both these designs and these designs. And then there was a couple of guys called Lawyer and Needham. They wrote a paper on the duality of operating systems, and this is the point they made. Okay, this is a classic paper. When wherever there's a PhD exam in operating systems, you're supposed to know this paper. Okay, if there's one classic paper, this is the one. And this is the finding that look, they're really duals of each other. Okay. So you may not understand this, but you guys understand this at least. Most people understand this and not this. Okay, but this is what you guys have to do in Java anyway. And I've just used different syntax to show you what this means. So, but you guys know wait and signal conditions well? Let me just. So what does notify really mean?
Whoever is make one that's waiting and tell it to wake up.
At what point? So supposing I'm executing inside this.
At the point of termination of that. When I release my lock, any thread not notify all, one thread should wake up and attempt to acquire this lock once I release it.
And I release it when I do condition or when I return from the method?
When you return.
That is Java, okay? So why did I have to do a while there? Why did the guy who was waiting have to do a while?
Because if the other person didn't notify all, someone else could have acquired it.
Okay, so if I don't do notify all, okay? If I do just one notify? So...
And then maybe not. He still needs to check his conditions.
Sorry?
He still needs to check his conditions if he wakes up.
Because I did, when I went and said, when I went and notified, at that point the condition is true for him to proceed.
Yeah.
But at that point. And so if I'm not doing broadcast, why should that guy not?
Broadcast means that.
Yeah, forget broadcast for now.
Okay.
Broadcast is, is something that Java's putting. Just forget broadcast. And I don't know why I've got this program with broadcast. Okay, I should have just said. But assuming this is not broadcast, why does the other guy have to check? We still have to check.
It actually depends on the program that you're running.
It does, but in general, you should be checking.
In general, you should check.
Like another thread in conflict, yeah, forward back to
So, but only one thread will be there at one time. So if you're not broadcasting, you will wake up one thread. That thread will go and check the condition. Will go and proceed, right? So forget this broadcast part, okay? I think, I just did signal. I just did notify. One process woke up. Surely it can go and proceed. Why did it have to go and check one more time? It has to do with the fact that this condition, that The process enters not when this condition is signaled, but when the method returns. Between the time that I do the signal and I return, I might cause that condition to get false. That's called the hint semantics. Absolute semantics, which was what people first did, basically, whoever did the signal was bumped out of the monitor. The signaled process executed it, and then they returned. This guy typically went right back into the monitor to come back, because typically this was the last statement. Okay, so that's what's going on with monitors. Okay, and you can look at this, and you can look at this, and a lot of people like this much better. Okay. So when you guys see these receives, and you say, why is receive a statement? Why is it just not a declaration or a procedure? You see what you can gain from this. Okay, and just to sort of give you now, so procedure entry. So the classic term for synchronized methods is entry procedure. So calling the entry procedure is equal to sending a request message to the send port. Okay. So flexibility comparison. The guard is evaluated once at the start. That's it. Okay, so it's not as if you can do waits at multiple points in the method. So the monitor solution is far more flexible. Okay, you can have multiple waits in an entry procedure in general. Whether that's good programming or not, we can debate. But flexibility-wise, people, Loud and Needham did not mention this point, but there is this difference. Okay. There's one signal which is return, saying at this point, please, all the waiters check, check for each of the waiter system which one is true, and it picks up one non-deterministically. Whereas here you can have multiple signals in a method also. Okay, so this is a little bit more chaotic, more flexible, and do we need the extra monitor flexibility? Okay, I mean, my guess is no. Okay. So all the classic problems, readers, writers, and all have been done using guards, from what I remember. So at least the classic problems you could do, even though theoretically the flexibility is less. Okay? Okay. So there's a whole question of should we have implicit receive or explicit receive, okay? And like I said, it seems like receive for procedure calls, explicit receive for procedure calls seems all unintuitive. But now you see that when that receive is a sync receive, you can do interesting things with it. You can use synchronization. And going back to Asad's question also that, why is the most interesting point the point at which the method finishes? Why can't the semantics of the application be dependent on when the buffers got emptied? Okay, and you were saying that, look, that also can influence the semantics. People said synchronous send is when the procedure finishes or when the assignment finishes, because they wanted to build such synchronization into their programs. So because they wanted to compete with monitors, it was when the assignment finished or when the procedure call finished, that was when the operation was supposed to finish, and that was when you were supposed to unblock to simulate such problems. Okay, so that's why those semantics were chosen.
Not necessarily exit the method, just exit the synchronized portion, relinquish your log, because in that particular example, the entire method is synchronized.
Yeah.
But you could have a synchronized something else, and then whenever you exit the synchronized.
So you're saying, but that is still something in your code, not something that's happening in the buffers.
Yes.
Okay. So that I grant you that you can go and return signal multiple times, wait multiple times, and you can have synchronize multiple times too. I grant you that. That's more flexibility. Okay. But why is it that when you have synchronous send, it is supposed to finish when the operation completes rather than when system buffer gets? Because you're saying that also could be used to change the semantics of my application. Okay. And I'm saying, yeah, you could imagine creative applications where that's the case. But if you want to go and simulate, what monitors do, this is more meaningful. Okay. But usually there is implicit receive for RPC and explicit receive for remote assignment, even though in ADA we saw explicit receive for for procedure calls also. And we saw how that could be used for synchronization. Okay. That was a complex argument, and we're out of time, and we should take only about 3 or 4 minutes to finish. Everything else is simpler, but that was sort of the complex part. Okay. So we're looking at various issues in IPC design, and we're trying to come up with a dimensional space. And when you talk of concrete systems, things become easier to grasp because you see all the features next to each other, and you just see how this feature implies this feature, and it's all a coherent whole. When you do design space, it becomes more tricky because you're saying there are all these possibilities, and then you say, but you know what, this possibility and this possibility maybe don't go that well together, and these go well together. So it becomes far more abstract, and I think it became a little on the high abstraction side last time. Okay. Just because we were looking at all the interaction between buffering and asynchronous, and those are important issues, though. Okay, so that's the kind of discussion I think I do have to some extent in those operating system notes. I haven't taught operating systems for a while now. Okay, so they're very dated, and I did focus here more on distribution and there more on OS. So there's that difference. Okay, so just now things become a little simpler. So we have this IPC design space, and by process I meant really a process within a heavyweight process or a heavyweight process in its own right. Okay, so a thread and process for both processes, and there's reason to have IPC among any kind of process. And let's kind of see why and what this location of communicating threads means. So ultimately, there's going to be some threads communicating, whether they're in 2 different address spaces or a single address space. Okay, so the question is where are the threads? And one approach is that the threads are all in one address space, one process. And when I talked about the Xenu implementation, I talked about this kind of threads. And so why would Xenu, or why would any system that has multiple threads support inter-process communication, inter-thread communication, given that we have shared memory? I mean, in the case of heavyweight processes, there's no shared memory. So yeah, we need inter-process communication. But here? Synchronization. Okay, we saw last time with guards that you might want to do synchronization, but if you have monitors and modules, you still want that. You like that guards better than the conditions. Guards are better. Or condition variables are better. Conditions are better. Why, by the way?
They're more general.
They're more general, but do you want the generality? Do you want the generality? I'd be very curious for you to come up with some application, and I'm sure these exist, where guards would not suffice and monitors would, conditions would suffice.
Guards only prevent assignments until certain conditions.
No, not just assignments, depending on the IPC, right? If the IPE is remote procedure call, then guards stop that procedure from being called. That's how we went and stopped the producer from overproducing and the consumer from overconsuming. So when the duality paper was written, they didn't go and say that one is more general than the other, from what I remember. But if you look at it deeply and you sort of try to look at the correspondence, the monitors are more general. And so you like monitors. So this is even less reason to have inter-thread communication in some sense, right? And yet a lot of operating systems do have.
Talk to each other in the same manner the processes talk to each other.
Okay. There's more uniformity. In fact, in the OS course I taught, they would first build intra-process, inter-thread communication. They would take the same API, exactly same, and make it distributed. Okay? So there's uniformity. You're going to need communication, and maybe you will take 2 things that are heavyweight processes and just transfer them into 2 lightweight threads, maybe. Other reasons? Think of duplex ports, simplex ports, input ports. So if you have shared memory, how many threads can access it? Well, you can do some package level stuff, okay? But it's global memory. And people argue against global memory a lot. Okay?
Just do public private key pairs between all bits.
Huh?
So I just do public private key pairs between all bits.
So, you know, there's the global memory issue, yeah. And there's all these locking issues that arise then. So you know, avoids global memory. Okay. So, do you guys know of OSs that have threads and inter-thread communication? I mean, do you know what happens in Linux, for instance? So I can tell you historically, I told you as a grad student, we guys built a distributed operating system. And one of those guys, John Kepix, and one other person, they went to Sun. And there we had inter-thread communication. They went to Sun and built lightweight processes, threads into the Sun kernel with communication. Okay? And there was one scheduler thread, and there was one memory management thread, and there was all the various memory, all the various. You know, this was the time when modules and objects were not so much in vogue, and especially in the kernel level, it was C. So C doesn't come with, you know, monitors and so forth. So threads was something you could add on it. And so I know at Solaris had threads. Okay? I don't know what's happening in Linux, and I won't be surprised if they have threads in the kernel with inter-thread communication. Okay? So then there is intra-computer message passing, where processes within the same computer can communicate messages using some abstraction, but processes on different computers can't. And you guys know of such an abstraction? Software interrupts, very good, very good. Yeah, ask him questions on Saturday. He's paid attention. And somebody who's even paid more attention? Pipes. Right? So.
The pipes support communication between.
Well, you think so, yeah, because there's file descriptors, so you could.
Yeah, but you know, there's named pipes and non-named pipes, and I'm talking about non-named pipes. Okay? And actually, pipes, as they were first created, you know, didn't do this. Then came sockets. And after sockets came, pipes got implemented on top of sockets. So it's all the more reason for them to support intercomputer. Okay. But the basic notion, but for you to just pipe the output of one process to a process in another machine, okay, is just not done. I mean, it's you know, you can do it through the pipe, but there's no command interpreter that does it. And you know, if you do this whole notion of automatically two processes that don't know of each other being connected together can only happen as long as they're being forked by a single process. Otherwise, you can use named pipe, but you have to do the pipe call. You have to go and close one descriptor, open another descriptor. So this transparency only comes within a particular computer. Okay, but I think software interrupts is a better answer. And then of course there's intercomputer message passing. And you know, there's all kinds of applications for this. Okay. So there's reason to have different kinds of locations. And the more flexible and distant the message passing, you know, the more complex the API and implementation. So the other thing is that, you know, and you sort of see in the next issue, how do you name a port? And, you know, we said, okay, the thread sends message to a port, another thread receives message from a port. And this is a very logical idea, and I just drew a picture, and I didn't, you know, I didn't really go down into details. But, you know, what is port as an abstraction? If it's a single object shared by both of them, then that kind of implies that the two threads are in the same memory, right? Same address space. The moment they start going to different address spaces, we have to have different handlers, different objects in a local address space that together name one logical entity, right? And when they together name one logical entity, we need to somehow agree on some naming that is beyond variables in memory. We have to worry about some inter-process naming. So intra-process address space communication, you know, we can just use one port handle for both, okay? And in the case of Xenu, we saw that port handle was just the PID, in fact. Okay, that the PID was used by both of them. And CSP. Xenu actually, the receiver never named a process. The receiver just said, I'll receive from anybody. But in CSP, you said, I want to send message to this person and I'm receiving message from this person. So that's how you created a bound port. So you just, this was all port handle. Intracomputer, you could have a port handle that is inherited by the two children, okay, which would mean it's a file descriptor. So it's like shared memory, except that, there is some indirection level, and the file table goes and has an index that gets translated into some operating system data structure that is shared between them. Okay? So in the address space of the process, there are two different data structures. One says ID1, one says ID3, but both of them point to the same data structure in the kernel, so they refer to the same thing. Okay? So that's an intracomputer. And this is like sort of files that are inherited. And in general message passing, you've got to have some external name that is, and that's why I named pipes or these general sockets, where the port has a name that is independent of any address space, okay, and independent of any OS tables, independent of any process address space. And you have to go and connect, somehow bind them together. So you cannot inherit from common parent. You need an external name. And, we saw that, the naming could be done per message. Okay? So at each message sending time, you go and say, that guy. Right? And that is provided by who? We saw this. Datagram. Registration means some kind of session established, right? Datagram says, look, every time I'm going to name that machine and name that port. Okay? And when I do send, I say send to. But this whole idea of naming each time means that there's no connection between the various messages. There's no stream or connection-based communication. And so, and if there's going to be some access control done, it'll have to be done on each message. So if we want to allow the process to only retrieve data from us but not change data, we'd have to go in at every message say that, is that the same right kind of request. There's a nice thing about handles. When you say open a file, you open a file for two reasons, right? You open a file, one is that I don't want to name the file every time. Okay? And it'll be also nice that if the OS doesn't have to go and name the file to a inode each time. But this is also an access control reason when you open a file. So when I open a file, I say open file name, comma, the access rights. At that point, the OS says, okay, do you have those rights or not? And if you do, I'll give you a handle. If you don't, I'll complain. And then on each access to the file, it says, if you couldn't have been using it in the wrong way. So you just have to go and check at that point that what you asked for, the rights that you said you will use are the ones you're using. It doesn't have to go and check whether you have those rights or not. It doesn't have to go to the file and see whether you're in the list or not. It says, okay, you said read only. I established you can do read, so I'll allow you to do it, and now I have to only check. Okay, so these things are called capabilities, where you get some kind of token that authorizes you, and you don't have to do a lookup each time. Okay, so that's the kind of thing with when you bound it to a handle. Okay, and then you use the handle again and again. Okay, and now we can use a registration also and say that how did you discover the name and get a handle, and you can get the handle yourself, but you can just say bind. The OS can just go and do it for you, or you can go to a name server where a handle is provided and get the handle from there. Okay, so the idea there is that you have more flexibility. You're not bound. Same name can be used by multiple registrars. Okay, so if I want a file server, if I do it, if I make my OS determine what my name should be, what name should be mapped to what name should be mapped to a service, it has to go and decide this is the file server, and it goes there. There, any file server can go to the registry and say, I'm the file server, and somebody can say, no, I'm now the file server, and you can pick up the latest one, or you can pick up someone based on some other attributes in the registry. So there's more flexibility having a registry. Okay. So in the case of Java RMI, you see that there's an external name server to which you go to figure out which you want to go to. So non-connection based IPC can use any of these mechanisms. I can always sort of have a library that goes and takes an external name and binds it to a handle, and every time I use that handle, it can go and then send the external name across. Okay, so you can always use handles for datagram, for non-connection based things. But connection based communication implies handles, okay, because there's a continuity. Okay, so that's my design space. And we saw that IPC could be shared memory, okay, software interrupts. So, and we didn't call software interrupts IPC actually, we just called it, message passing, we called it IPC. Okay? And then there was message passing, where we talked about ports and messages being exchanged between processes, and then we saw all kinds of choices. Are those reliable or not reliable? You don't get those issues in shared memory. Okay? In order, access, routing, are we doing RPC, or are we doing remote assignment? Are we sending a byte, a block, or an object? If we are doing assignment, if we are doing, if you're sending data, you know, how big are the buffer sizes kept in the application space, in the kernel space? You know, when do you block until, and especially in the case of send, do you have language support? Do you not have language support? You know, if you don't have language support, you can't do object communication. And do you have explicit receive, or is it implicit receive? And if it's explicit receive, what are the receive blocking times? And if the receive doesn't block, it becomes a lot like implicit receive, except that implicit receive says, I'll receive anything, any number of receives from now on at this point. With implicit receive, you say, okay, I'm ready to receive one more message. Here's my transaction. Here's the transaction ID. Give me a transaction ID for that one. I'm ready to receive another message. Give me a transaction ID for that one. And I can then wait on that transaction ID if I want. Okay? And in the OS that we guys built, we did have this kind of receive. So this is not totally theoretical. Okay? Location of communication threads, naming. Do we have a reply or not? Is there a reply block or not? You know, so there's, you know, if you're going to design a system, there's a lot of decisions you have to make. Okay? So if you design a programming language, it's hard enough. If you build a distributed programming language, it becomes even harder.